Algebraic geometry is a branch of mathematics, classically studying zeros of multivariate polynomials. Modern algebraic geometry is based on the use of abstract algebraic techniques, mainly from commutative algebra, for solving geometrical problems about these sets of zeros. The fundamental objects of study in algebraic geometry are algebraic varieties, which are geometric manifestations of solutions of systems of polynomial equations. Examples of the most studied classes of algebraic varieties are plane algebraic curves, which include lines, circles, parabolas, ellipses, hyperbolas, cubic curves like elliptic curves and quartic curves like lemniscates, and Cassini ovals. A point of the plane belongs to an algebraic curve if its coordinates satisfy a given polynomial equation. Basic questions involve the study of the points of special interest like the singular points, the inflection points and the points of infinity. More advanced questions involve the topology of the curve and relations between the curves given by different equations. Algebraic geometry occupies a central place in modern mathematics and has multiple conceptual connections with such diverse fields as complex analysis, topology and number theory. Initially a study of systems of polynomial equations in several variables, the subject of algebraic geometry starts where equation solving leaves off, and it becomes even more important to understand the intrinsic properties of the totality of solutions of a system of equations, than to find a specific solution. This leads into some of the deepest areas in all of mathematics, both conceptually and in terms of technique. In the 20th century, algebraic geometry split into several sub-areas. The mainstream of algebraic geometry is devoted to the study of the complex points of the algebraic varieties and more generally to the points with coordinates in an algebraically closed field. The study of the points of an algebraic variety with coordinates in the field of the rational numbers or in a number field became arithmetic geometry, a subfield of algebraic number theory. The study of the real points of an algebraic variety is the subject of real algebraic geometry. A large part of singularity theory is devoted to the singularities of algebraic varieties. With the rise of the computers, a computational algebraic geometry area has emerged, which lies at the intersection of algebraic geometry and computer algebra. It consists essentially in developing algorithms and software for studying and finding the properties of explicitly given algebraic varieties. Much of the development of the mainstream of algebraic geometry in the 20th century occurred within an abstract algebraic framework, with increasing emphasis being placed on intrinsic properties of algebraic varieties not dependent on any particular way of embedding the variety in an ambient coordinate space. This parallels developments in topology, differential and complex geometry. One key achievement of this abstract algebraic geometry is Grothendieck's scheme theory, which allows one to use sheaf theory to study algebraic varieties in a way which is very similar to its use in the study of differential and analytic manifolds. This is obtained by extending the notion of point. In classical algebraic geometry, a point of an affine variety may be identified, through Hilbert's Nullstellensatz, with a maximal ideal of the coordinate ring, while the points of the corresponding affine scheme are all prime ideals of this ring. This means that a point of such a scheme may be either a usual point or a subvariety. This approach also enables a unification of the language and the tools of classical algebraic geometry, mainly concerned with complex points, and of algebraic number theory. Wiles's proof of the long-standing conjecture called Fermat's last theorem is an example of the power of this approach. Basic notions. Zeros of simultaneous polynomials in classical algebraic geometry. The main objects of interest are the vanishing sets of collections of polynomials, meaning the set of all points that simultaneously satisfy one or more polynomial equations. For instance, The two-dimensional sphere in three-dimensional Euclidean space R3 could be defined as the set of all points with a slanted circle in R3 can be defined as the set of all points which satisfy the two polynomial equations affine varieties. First we start with the field K. In classical algebraic geometry, this field was always the complex number C. But many of the same results are true if we assume only that K is algebraically closed. We consider the affine space of dimension n over K, denoted n. When one fixes a coordinate system, one may identify n with knots. The purpose of not working with knots is to emphasize that one forgets the vector space structure that knots carries. A function f. An A1 is said to be polynomial if it can be written as a polynomial, that is, if there is a polynomial p in K, x1, xn, such that f equals p for every point n with coordinates in n. The property of a function to be polynomial does not depend on the choice of a coordinate system in n. When a coordinate system is chosen, the regular functions on the affine n space may be identified with the ring of polynomial functions in n variables over K. Therefore, the set of the regular functions on n is a ring, which is denoted K, n. We say that a polynomial vanishes at a point if evaluating it at that point gives 0. Let S be a set of polynomials in K, n. The vanishing set of S is the set V of all points in n where every polynomial in S vanishes. In other words, a subset of n which is V, for some S, is called an algebraic set. The V stands for variety. Given a subset U of n, can one recover the set of polynomials which generate it? If U is any subset of n, define I to be the set of all polynomials whose vanishing set contains U. The I stands for ideal. If two polynomials f and g both vanish on U, then f plus g vanishes on U, and if h is any polynomial, then hf vanishes on U. So I is always an ideal of the polynomial ring K, n. Two natural questions to ask are: given a subset U of n, when is U equals V? Given a set S of polynomials, when is S equals I? The answer to the first question is provided by introducing the Czarsky topology, a topology on n whose closed sets are the algebraic sets, and which directly reflects the algebraic structure of K, n. Then U equals V, if and only if U is an algebraic set or equivalently a Czarsky closed set. The answer to the second question is given by Hilbert's Nullstellensatz. In one of its forms, it says that I is the radical of the ideal generated by S. In more abstract language, there is a Galois connection, giving rise to two closure operators. They can be identified and naturally play a basic role in the theory. The example is elaborated at Galois connection. For various reasons we may not always want to work with the entire ideal corresponding to an algebraic set U. Hilbert's basis theorem implies that ideals in K and are always finitely generated. An algebraic set is called irreducible if it cannot be written as the union of two smaller algebraic sets. Any algebraic set is a finite union of irreducible algebraic sets, and this decomposition is unique. Thus its elements are called the irreducible components of the algebraic set. An irreducible algebraic set is also called a variety. It turns out that an algebraic set is a variety if and only if it may be defined as the vanishing set of a prime ideal of the polynomial ring. Some authors do not make a clear distinction between algebraic sets and varieties and use irreducible variety to make the distinction when needed. Regular functions, just as continuous functions, are the natural maps on topological spaces, and smooth functions are the natural maps on differentiable manifolds. There is a natural class of functions on an algebraic set, called regular functions or polynomial functions. A regular function on an algebraic set V contained in n is the restriction to V of a regular function on n. For an algebraic set defined on the field of the complex numbers, the regular functions are smooth and even analytic. It may seem unnaturally restrictive to require that a regular function always extend to the ambient space. but it is very similar to the situation in a normal, topological space, where the TS or extension theorem guarantees that a continuous function on a closed subset always extends to the ambient topological space. Just as with the regular functions on affine space, the regular functions on V form a ring, which we denote by kV. This ring is called the coordinate ring of V. Since regular functions on V come from regular functions on them, there is a relationship between the coordinate rings. Specifically, if a regular function on V is the restriction of two functions f and g in K, then f minus g is a polynomial function which is null on V and thus belongs to I. Thus kV may be identified with K and I. Morphism of affine varieties. Using regular functions from an affine variety to A1, we can define regular maps from one affine variety to another. First we will define a regular map from a variety into affine space. Let V be a variety contained in n. Choose m regular functions on V, and call them f1, fm. We define a regular map f from V to m by letting f equals. In other words, each phi determines one coordinate of the range of f. If V is a variety contained in M, we say that f is a regular map from V to V, if the range of f is contained in V. The definition of the regular maps apply also to algebraic sets. The regular maps are also called morphisms, as they make the collection of all affine algebraic sets into a category, where the objects are the affine algebraic sets and the morphisms are the regular maps. The affine varieties is a subcategory of the category of the algebraic sets. Given a regular map G from V to V, and a regular function f of k, V, then fg k, V. The map ffg is a ring homomorphism from k, V, to k, V. Conversely, every ring homomorphism from k, V, to k, V, defines a regular map from V to V. This defines an equivalence of categories between the category of algebraic sets and the opposite category of the finitely generated reduced K algebras. This equivalence is one of the starting points of scheme theory. Rational function and birational equivalence contrarily to the preceding ones. This section concerns only varieties and not algebraic sets. On the other hand, the definitions extend naturally to projective varieties, as an affine variety and its projective completion have the same field of functions. If V is an affine variety, its coordinate ring is an integral domain and has thus a field of fractions which is denoted K and called the field of the rational functions on V, or, shortly, the function field of V. Its elements are the restrictions to V of the rational functions over the affine space containing V. The domain of a rational function f is not V but the complement of the subvariety where the denominator of f vanishes. Like for regular maps, one may define a rational map from a variety V to a variety V. Like for the regular maps, the rational maps from V to V may be identified to the field homomorphisms from K to K. Two affine varieties are birationally equivalent if there are two rational functions between them which are inverse one to the other in the regions where both are defined. Equivalently, they are birationally equivalent if their function fields are isomorphic. An affine variety is a rational variety if it is birationally equivalent to an affine space. This means that the variety admits a rational parameterization. For example, the circle of equation is a rational curve, as it has the parameterization which may also be viewed as a rational map from the line to the circle. The problem of resolution of singularities is to know if every algebraic variety is birationally equivalent to a variety whose projective completion is non-singular. It has been positively solved in characteristic 0 by Czarsky-Topology in 1964 and is yet unsolved in finite characteristic projective variety, just as the formulas for the roots of second, third and fourth degree polynomials suggest extending real numbers to the more algebraically complete setting of the complex numbers. Many properties of algebraic varieties suggest extending affine space to a more geometrically complete projective space. whereas the complex numbers are obtained by adding the number I, a root of the polynomial x squared plus 1. Projective space is obtained by adding in appropriate points at infinity, points where parallel lines may meet. To see how this might come about, consider the variety V. If we draw it, we get a parabola. As x goes to positive infinity, the slope of the line from the origin to the point also goes to positive infinity. As x goes to negative infinity, the slope of the same line goes to negative infinity. Compare this to the variety V. This is a cubic curve. As x goes to positive infinity, the slope of the line from the origin to the point goes to positive infinity just as before. But unlike before, as x goes to negative infinity, the slope of the same line goes to positive infinity as well, the exact opposite of the parabola. So the behavior at infinity of E is different from the behavior at infinity of E. The consideration of the projective completion of the two curves, which is their prolongation at infinity in the projective plane, allows to quantify this difference. The point at infinity of the parabola is a regular point, whose tangent is the line at infinity, while the point at infinity of the cubic curve is a cusp. Also, both curves are rational, as they are parameterized by x, and Riemann-Roch theorem implies that the cubic curve must have a singularity, which must be at infinity, as all its points in the affine space are regular. Thus many of the properties of algebraic varieties, including birational equivalence and all the topological properties, depend on the behavior at infinity, and so it is natural to study the varieties in projective space. Furthermore, the introduction of projective techniques made many theorems in algebraic geometry simpler and sharper. For these reasons, projective space plays a fundamental role in algebraic geometry. Nowadays, the projective space Pn of dimension n is usually defined as the set of the lines passing through a point, considered as the origin, in the affine space of dimension n plus 1, or equivalently to the set of the vector lines in a vector space of dimension n plus 1. When a coordinate system has been chosen in the space of dimension n plus 1, all the points of a line have the same set of coordinates, up to the multiplication by an element of k. This defines the homogeneous coordinates of a point of Pn as a sequence of n plus 1 elements of the base field k, defined up to the multiplication by a non-zero element of k. Given a polynomial in n plus 1 variables, it vanishes at all the point of a line passing through the origin if and only if it is homogeneous. In this case, one says that the polynomial vanishes at the corresponding point of Pn. This allows to define a projective algebraic set in Pn as the set V where a finite set of homogeneous polynomials, f1, fk, vanishes. Like for affine algebraic sets, there is a bijection between the projective algebraic sets and the reduced homogeneous ideals which define them. The projective varieties are the projective algebraic sets whose defining ideal is prime. In other words, a projective variety is a projective algebraic set, whose homogeneous coordinate ring is an integral domain. The projective coordinates ring being defined as the quotient of the graded ring or the polynomials in n plus 1 variables by the homogeneous ideal, defining the variety. Every projective algebraic set may be uniquely decomposed into a finite union of projective varieties. The only regular functions which may be defined properly on a projective variety are the constant functions. Thus this notion is not used in projective situations. On the other hand, the field of the rational functions or function field is a useful notion, which, similarly as in the affine case, is defined as the set of the quotients of two homogeneous elements of the same degree in the homogeneous coordinate ring. Real algebraic geometry. The real algebraic geometry is the study of the real points of the algebraic geometry. The fact that the field of the Rayleigh number is an ordered field may not be occulted in such a study. For example, the curve of equation is a circle if, but does not have any real point if. It follows that real algebraic geometry is not only the study of the real algebraic varieties, but has been generalized to the study of the semi-algebraic sets, which are the solutions of systems of polynomial equations and polynomial inequalities. For example, a branch of the hyperbola of equation is not an algebraic variety, but is a semi-algebraic set defined by an or by an. One of the challenging problems of real algebraic geometry is the unsolved Hilbert's 16th problem. Decide which respective positions are possible for the ovals of a non-singular plane curve of degree 8.